Alright, so let me continue here. Let's jump straight into it and try to explain to you a little bit more about why the tangent space is a vector space. So if you look at section 4.2, I give an argument here which basically explains why, if you look at an implicitly defined surface, if you're given two vectors in the tangent space, in other words, they're velocity vectors for curves, then you can construct a third curve which takes the sum of the vector, which has as its velocity vector the sum of the two vectors that you're given, and you can construct another curve which has a scalar multiple of the velocity vector that you're given. And the argument's down here, and it's a little bit sneaky. I'll let you read this. I mean, I'd be happy to talk to you about it in office hours. I think it makes sense, but it's a little bit involved. Here's basically the picture. The picture of the proof is basically this. You have this one curve, and you've got another curve, right? And the red curves have like v1 and v2x as the x parts of the velocity of these two things. And I mean, there's also a y part because it's not a horizontal vector up here, but the y part is completely determined by the graph, which solves this solution set locally. So like essentially these vectors are fixed by their horizontal pieces. And then down here in RK, you can build the sum vector from these two like that. And then if you just basically take the line which is built, or you can even take I was a little bit greedier in this picture. It's v1x plus c times v2x. So this is like not just the sum of these two, but like a linear combination of these two. Then if you take this line down here, you can use the patch you can construct from the graph of this thing. And you can just take this curve and paste it up there. And when you do that, the velocity vector to this gamma will have that as its velocity vector. And consequently, you'll be able to get another curve. So given two vectors in the tangent space, you can construct another curve which takes the sum, or in fact the linear combination of those two vectors as its tangent vector, which is to say, if we define the tangent space, right? Let me remind you here's the definition. So here I give it for level set. If we have this is just a funny fancy notation for the solution set of g of x equals to c, right? Then we can define the tangent space at P to be the set of pairs, P comma V, such that V is the velocity vector of a differentiable curve where gamma of 0 is P and V is that gamma prime of 0. And we, like I told you guys, we did define addition and scalar multiplication by just doing it on the vector part. In fact, the next page, I think I even tell you more. I tell you we can define dot products and even norms by just doing it on the vector part. We can say two vectors are orthogonal. And so we take the set of all vectors with a p attached to be called VP. That might include more than just tangent vectors. We could look at vectors which are not don't appear as tangent vectors. For example, if you were looking at this, just to give you a simple example, if you were thinking about the space to be xy plane, the tangent space at a point in the xy plane would just be horizontal vectors, but then the whole VP would also include the vertical vectors. I'm getting off topic here. Anyway, we'll get back to looking at the relation between the velocity vectors to curves and the derivative of the level function when we talk about Lagrange multiplier. So I'll save that for there. Anyway, long story short, what we prove in this here is that for a level set, we can either look at we can define the tangent space and the null space, and we can calculate them. So like the null space is directly given by the just attaching the column space of the Jacobian matrix transposed, which is nice. On the flip side of things, the tangent space is given by the null space, all right, which is, if you want to describe explicitly, that's the calculation I was talking about earlier in this thing. These two things together give you the whole set of vectors at P, which we could just say, I guess you could just say RK plus P here if you wanted. Okay, now I have a couple of, I think these are good examples to look at. They should help you, I think, understand things here. But then, here's the rest of the example. Then, of course, I start talking about how you found the tangent normal space from patches, right? So I gave you guys an example of a patch versus the level set last time. And long story short, here we can either, the tangent space is easy to calculate. It's just we attach the column space of the derivative matrix to the point, or to find the normal space, we have to do this calculation. So the tables are turned. Null space is easy to calculate for the implicitly defined one, whereas the tangent space is easy to calculate for the patch. And so there's always these competing factors here. So like here's an example. This is actually a surface in R3. XY goes to XY, 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 yeah, okay, sorry, it's all. Then the derivative matrix is just this, 1, 0, y, 0, 1, x. So if we pick this point, a comma b comma a, b, and s, the tangent space to p at s would be given by a, b to this point, and then we attach the span of these two things. So 1, 0, b, 0, 1, a, that's the tangent space. The normal space we find from the usual kind of calculation. So we want to calculate the null space of this, and it works out to be the span of minus b minus a1. Of course, you could also just say, I want a vector which is perpendicular to these two, right? Clearly this dot product that is 0, this dot product that is 0. Now could you guess this from these two? I don't know. I'm sure all of you could take the cross product of these two and get something like that, right? But anyway, that is the direction vector to the normal line, is what that is, geometrically. Another example, here's the normal space in all of its pedantic glory. Here's another one. From R2 to R4, we have this patch, all right? Here's its Jacobian matrix, so the columns are partial velocities. And if we pick that point, then we get this tangent space. You can calculate the normal space by, you plug in the point and go through that normal space calculation. You get span of this and that. And you can see that this and that and that and that are perpendicular. The normal space is given by that. So there it is. All right. So just to summarize, we can describe a manifold, or a set if you like, a k-dimensional, really manifold's a better word here, manifold of dimension k. We can either describe as being given by a patch, where we have these partial derivatives are, oh sorry, the t is weirding me out. The derivatives of the, good grief, the columns of the Jacobian matrix of the patch are linearly independent. And you got, k of them. And they have to be linearly independent at each point in the domain, all right? Or you can have that the rank, now notice I've used f here, which is unfortunate. I was using f for the patch last lecture. Here I'm using f for the level, this is horrible. I really should be using g here. This is bad, because this is supposed to be the level equation, all right? But anyway, I can get over my notation for a second here. So if we have that has rank p, then in other words, you always have genuinely p independent equations from f of x equals to c, Then that's another way we can describe, of course, a k-dimensional manifold. And then depending on which viewpoint you use, you can either describe the tangent space this way, or you describe the tangent space in the more awkward way here. You have to actually calculate the perp for the implicit viewpoint. Conversely, to calculate the normal space to the patch, you actually have to calculate the perp, whereas if you want to calculate the normal space to an implicitly defined function, we just look at the row space, and that will do it. All right. So I wanted to just, this is not in my notes, but I thought it'd be helpful. Possibly. Possibly not. Let me try to get on with it here. Let me zoom out a bit. So I wanted to just try to talk through the idea of the tangent space and why it's a vector space just a little bit more, because, you know, I think it's kind of important. So, I mean, we'll be talking about tangent space in a much more abstract way before you know it in that book that we're going to use. So I think it's good to just take a moment here to try to think about these things more sort of directly in terms of geometry in Rn. So I'll try to do that here. So here's the theorem. If we have a patch of a k-dimensional manifold inside Rn, in other words, the rank of this map is k for all points in the domain of the patch, then it has a k-dimensional tangent space. And in particular, the tangent space is really just p cross the column space of R prime at u0, where R of u0 is p. In fact, we can find an isomorphism, a vector space isomorphism between that guy and that guy. And the vector space isomorphism is essentially drop the p. Okay, now it's not. It's a little bit more than that, because this is a set of k linearly independent n-dimensional vectors. So, okay, fine. But here's a picture, an attempt at a picture anyway. So here's my parameter space, and I've got the u1 through, let's say, u2 through uk variables in the domain of the patch. These are the parameters. My patch takes me over here, takes this, and this over here is actually the manifold in Rn, M. And so here's the idea. I want to study the tangent space to that point. I have to think about all possible tangent vectors to that point, right? The tangent space is formed by all possible tangent vectors to the point. So how do you get a curve over here? Well, one way you can get a curve up here to calculate a tangent vector to is to take a curve over here in the domain of the patch and just kind of move it over. So this is the idea. I take a curve here, or path really, from R to up here, sigma of t, and I take that, I feed it to R, and that gives me a path up here. Basically, sigma takes the real line and pastes it in U, and then R takes this curve and pastes it over here. So it's all cutting and pasting. But anyway, so I'm assuming that sigma of 0 is u0, and I'm assuming that R of u0 is p, just that's the setup. So R of sigma of 0 is p. And so here's a point on the real line t that maps to sigma of t, and then under R that maps to R of sigma of t, which I'm calling gamma of t for the sake of discussion. I'm also using E1 for the standard basis here, whereas I'm using E1 bar and E2 bar for the standard basis over here. But now that I'm thinking about it, these never came up anywhere else, but I'm just saying, if you wanted to have another notation to distinguish between the standard basis in the target space of the patch versus the domain of the patch, by the way, this is sometimes called target space. The manifold sits inside the target space. So here it is. Gamma prime of 0 will be ddt of this composite, right? But by the chain rule, that's that, which is that. And then if you start thinking about it, if I just choose the right sigmas, right, then this is like vector times matrix. And if I make this like E1, it picks off the first column. If I make this E2, it picks off the second column. If I make this E3, it picks off the third column, and so forth, right? So then to do that, you just construct these like, coordinate curves in the domain. I called them sigma sub j just to give them a name. But like sigma sub j would be u0 plus tej. And this is fixing everything but just moving along the jth direction up here. And so like sigma prime of 0 is ej. So I can also define gamma j in the same way by just feeding sigma j to the patch. And then like gamma prime j of 0 would be this, but that's the jth column, right? So that's kind of the genesis of like how to study. That's how I think about putting together vectors over here and how they relate to the patch. So if I actually had an explicit patch, I could really go through what I'm saying right now to explicitly construct the subspace of Rn, which forms the tangent space to this surface, you know? Sorry, off the tangent space to this surface. All right, so in particular, here's the basic argument for closure of the vector space. Suppose we had gamma of 0 is p and alpha of 0 is p, and I've got gamma prime of 0 is v and alpha prime of 0 is w. Another way to say this would be, suppose I've got v and w in the vector space at p to the manifold. Then that means that there exists a curve gamma and alpha such that this happens, okay? Well, then I'd like to find, oh, first of all, notice that that means that v and w are in the column space by this calculation up here. This says that any vector is in the column space because this is a linear combination. You got to understand, guys, this is nothing more than linear combination of column vectors, right? Linear combination of column vectors in R prime naught. So clearly v and w are in the column space of R prime and v naught, which means if I make this my notation for the columns, that I can build v from this linear combination of columns, and I can build w from that linear combination of columns, where I'm using v sub I and w sub I for the numbers which build that linear combination. Basically, vi and wi are coordinates with respect to the sort of natural basis for the column space, just the columns of the Jacobi matrix. Then, check it out. If I make gamma tilde the curve, which is r of u naught plus t times, what do? I just take these coordinates, all right, and I build the corresponding vector down in the parameter domain. Like I build this, I take these vectors and I put them here, basically. What, and, well, it's not quite that, but what else would you do? I mean, I'm sorry, that's not a good reason. My apologies. So I take the coordinates from the given vectors and I just build this line down in the domain of the patch, and then it's fairly easy to see that because of the calculation that I just gave here, that gamma tilde prime of 0 will be CV plus W, which goes to show you that the linear combination of two vectors in the tangent space is again in the tangent space, right? Because to be in the tangent space, you have to be the velocity vector to a curve which lies on the manifold, right? And I've tried to describe how that works either from the implicit or the parametric viewpoint. I hope I've done some justice to it. There's probably more in McNerney, so we'll wait for there. But that's about all I have to say about this. I think I've told you guys enough to work some problems. I hope you're as excited as I am about being able to describe arbitrarily dimensional manifolds and arbitrarily high dimensional contexts. It's kind of neat. And surprising application to this is maximizing functions bounded on one or more constraints. So we'll look at that next, Lagrange multipliers. Thanks, guys.